I think it started. Okay,
All right.
please.
Thanks a lot for the introduction. I'm happy to give this talk today. Um, yeah, just maybe a few words about myself. Uh, I have, over my career, worked in a variety of different areas and departments. So my PhD was in electrical engineering. Then for my postdoc, I was in the School of Computer Science. Then my first um, professor position was at Louisiana State University in physics. And now I moved back to electrical engineering at Cornell. And so the statement that makes is that our field of quantum information science is highly interdisciplinary. It spans multiple areas. And for me, that's made it really exciting because you get to learn about a wide variety of topics and potentially contribute to that you might not otherwise be able to if you were working on a particular area than, say, computer science or electrical engineering or physics or mathematics. And so that's one thing that's been really great. What I'm going to talk about today to you is a topic that I've learned about um, more recently in the past, say, 2 to 3 years. There's been a lot of excitement about this area of variational quantum algorithms. Traditionally, my strength has been in the area of quantum information theory. This is a topic on which I've written textbooks and I've taught for years. And that experience has been helpful for these other projects. So, part of the reason I got into this topic is that as a professor, one of my goals or one of my tasks is to serve students, and to be there as their advisor. And so many new students have come in, um, especially Dramil and Surya. They started with me at LSU and moved with me to Cornell, and they had strong interest in this topic. And so I became interested in it also. And what I'm going to tell you about today is the results of this was kind of a grand experiment for me. I've seen other groups have a large team project, and so I wanted to try it out. And so I've been meeting with our team over the past, let's say, 7 or 8 months. And then we worked hard to finish off these papers and posted them. So the first one, I believe, is the one that we call dual VQE, and I'll talk about that. And then the next one is something we called QSLAC. And both are related to this general concept of trying to solve semi-definite programs in a variational quantum algorithm way. Um, and something funny about these archive numbers is you'll notice that this one, you obtain from this one by doing a cyclic shift of the last 3 digits. I really noticed that recently. Okay, so this is our research team. We're at Cornell. We had two high school students, Ivy and Kathy, joined us for the summer. And then Hannah and Jenny are two undergraduate students at Cornell. Lashani's a PhD student. We went to a conference in Rome, New York. There's the Air Force Research Lab. It's a 2 hour drive. We went there to their conference for the summer. Jamil and Sawyer are PhD students. And Zoe is our colleague who's all knowledgeable of variational quantum algorithms and issues like barren plateaus, and was always helpful in our project to ask many questions that we didn't know the answer to at the time. Okay, so what is the motivation of this work? Optimization is an important task for which it's believed that quantum computers might provide a speed up. If you log onto Twitter, you'll see lots of discussions of this point. Um, some people strongly believe it. Some people will call others liars if they say that this will be possible. And so um, I don't know where to fall in on this. It doesn't seem to be ruled out. It seems like it's interesting to pursue from a scientific perspective. And so that was my attitude and perspective while doing this project. Okay, so among optimization problems, there are what's called semi-definite programs. And this is a particular class of optimization problems that are easier to analyze, and they are widely used by classical computers. You know, you can download from MATLAB a package called CVX from a professor at Stanford. It's widely used. Now in Python, you could download CVX-Py and evaluate semi-definite programs classically. And there's wide interest in them because they're used in many different fields. I listed these, but there's also finance. It's used there as well. And so there's a lot of interest in them. And then that brings to bear the question, can we use quantum computers to make them even faster? And so that was our question. And we wanted to understand whether we could do this in a variational way. There is a large body of existing papers on quantum algorithms for semi-definite programs in the fault-tolerant era. And you know, we listed those in our citation list of our paper on QSlack. So if you're curious about those, you can consult. I believe it's even in the second or third paragraph of our introduction. But here we wanted to focus on variational methods for doing so, and there's not much work on that topic. There's our work, QSlack. There's a prior paper I had with Drumil Patel, and there's another paper by someone named Taylor Patty and her colleagues. Okay, so what am I going to do in this talk? I'm not going to assume that you know semi-definite programming theory to begin with. I'm going to give you a little overview of that to start out, and then I'll talk about what we call the QSlack method for estimating optimal values of SDPs. Something I'll say from the QSlack method is it's a general approach. You know, when we did our experiments, we used parameterized quantum circuits to evaluate their performance, but there could be other methods for doing so. You know, for example, last night on the archive, there was a paper on generative, it was called GQE. And, you know, one thought I had is that even that method could be used in QSlack as well. So, okay, let's proceed. Start with some background on semi-definite programming. If you want to see more background, there's a textbook by Stephen Boyd and his colleague, I forget his first name, but I think it's Vandenberg. It's a very famous book called Convex Optimization. It's a free download. You can also consult lecture notes of John Watrous, who's an expert on quantum information, who played a major role in bringing semi-definite program theory into the analysis of quantum computing and quantum information science. Okay, so stated succinctly, if you consult Wikipedia, you'll see this kind of phrasing. An SDP involves optimizing a linear objective function. So already we see that the objective function is a simple form because it's linear. And then it's over the technical term is cone of positive semi-definite matrices and their affine constraints. Okay, so I'll show some math in a minute that explains what that means. A key concept in optimization, and especially in semi-definite programming theory, is that every optimization problem has a dual optimization problem. And this is one of the key things that we use in QSlack. And I'm going to tell you a bit more about that. But this duality theory is very powerful, both numerically and even analytically. You know, one thing I won't talk about today is that semi-definite programming can be used as a theoretical proof tool. And I've done that for a long time in quantum information theory to obtain bounds on communication capacities and other related optimization tasks. So the dual SDP involves the opposite kind of optimization. So for example, if the primal is a maximization, the dual will be a minimization. And what the dual gives you is a bound on the primal STP. And so I'll speak to that more as we continue. Okay, so what is an SDP mathematically? You can view it as it's an optimization problem where the inputs are Hermitian matrices. I'll call them A and B. They're Hermitian, so they're square. They don't have to be the same size. They can be different dimensions. And then here I'll use a formalism where we have a hermiticity preserving superoperator. That is a linear map that takes a Hermitian matrix as an input and outputs a Hermitian matrix. That's why it's called hermiticity preserving, because it takes as input Hermitian and outputs Hermitian matrix. Okay, so all that being said, this is what we'll take throughout the talk as the general form of a primal semi-definite program. So the input is A, that is going into the objective function. It's a linear objective function because it's just you multiply two matrices and take the trace. A you view as a constant. Its values are unchanging, right? And X is what you try to optimize over to make this as large as possible. This soup is there. It's a supremum. It's the same as for all our needs today. It's the same as maximizing. And the optimization is restricted to be over matrices that are positive semi-definite. So this notation is a shorthand notation to indicate that a matrix is positive semi-definite. That's equivalent to the eigenvalues of X being non-negative. So that's a shorthand we'll use throughout. This is another shorthand. So phi is that hermiticity preserving superoperator. It takes X as input and it outputs a Hermitian matrix. And then it's being compared with B. And what this is, it's a constraint. It's an inequality constraint. In this optimization, the only legitimate or feasible X's that are considered are those for which this constraint holds and for which this constraint holds. The meaning of this is you can interpret it as somewhat similar to what you do for real numbers. I should take the matrix B, subtract from it 5x, and then if that resulting matrix is positive semi-definite, this constraint holds, okay? And so this is also a shorthand for that. And this is something we'll use throughout. So the only X's that we consider in the optimization are those for which this constraint holds and this constraint holds. And subject to those two constraints, we try to make this objective as large as possible. Okay, so that's an SDP in a nutshell. The dual SDP, as we said, it's the opposite kind of optimization. It involves a minimization. And what you notice here is that what's in the constraint goes into the objective, and what's in the objective goes into the constraint here. And so that's a kind of symmetry that's called duality. And oops. Now we're trying to make this objective function as small as possible, subject to this constraint and this constraint. This map here with the dagger is called the adjoint of phi, and I'll talk about what that is. I believe it's on the next slide. Okay, so to describe what the adjoint is, you can think of it as being analogous to the adjoint or Hermitian conjugate of a matrix. So to define the adjoint of a superoperator, we'll recall this definition of the Hilbert-Schmidt inner product of two matrices. So you take one, the conjugate transpose, and multiply and take the trace. That gives you a number, and this satisfies the axioms for an inner product. Okay, so phi dagger is called the adjoint of phi, and it's defined to be the unique superoperator satisfying this equation. So, you have this form of the inner product, and then the adjoint is flipped and acts on Y, and then you get this number. And if these numbers are equal for all possible X and Y, then phi satisfies, then phi is the adjoint. Okay. And this is quite similar to how the adjoint is defined for matrices. If you were to place C and D with vectors and Y and X were to be vectors and phi were to be a matrix, this is the definition of the adjoint of a matrix. And so you can view this definition here as a generalization of that. And that comes up in this dual formulation. Okay. So what is the duality theory? As a reminder, this is where we define alpha, this is where we define beta. Alpha is the optimal primal STP value. Beta is the optimal dual STP value. And there's something called weak duality, which always holds. And that's this number is always less than or equal to this number. And that's quite powerful. And interestingly, the proof is so simple that I can show you it in one line here. Okay, so that's very nice. And I somehow find this very illuminating. So suppose that X and Y are feasible. So X satisfies this inequality and this inequality, and Y satisfies this inequality and this inequality. Then what I can do, I can plug in the objective function for alpha here and consider it for a feasible X. Now, X is positive semi-definite, and then this inequality is satisfied, so I can apply this inequality to conclude this trace inequality. So we get that this number is greater than this number, and then I can use the adjoint property to bring phi on X, okay? To bring phi acting on X. And now I can finally use the assumption that X is feasible and satisfies this constraint, as well as the fact that Y is positive semi-definite, to replace phi X by B in this inequality. And so those are some simple steps that just involve using linear algebra. But now what we conclude is that this number is less than this number for all feasible X and Y. So if I maximize over X here and I minimize over Y here, then the inequality still holds. And that's how we conclude that alpha is less than beta. Okay? So that's the key idea behind weak duality. And it's something that we use in QSlack. So just to give you sort of a preview of that, if you're trying to do this optimization, but you're not sure that you can actually find the optimal value, but you're sure you can make the constraints obeyed, then you'll get some lower bound on alpha. You'll get some value trace of AX right here, right? And you might not be sure how good that value is as compared to the optimal value, this alpha, right? So what you can do is you can also do the opposite optimization in the dual and try to make this as small as possible. And then even in this dual, you might not be able to exactly compute the optimal value, but you can use some heuristic to optimize over some set of Y operators. And then when you do so, you'll get an upper bound on this value and you can compare them. And depending on how close they are, it gives you like a quality check on the solutions. And so that plays a role in our idea behind QSlack and dual VQE. Okay. In many cases of interest, there's a technical condition you can check. It's called Slater's condition. And if that holds, then you can conclude that actually there's an equality, that the primal is equal to the dual. And that happens in many cases of interest. So it's something to keep in mind. Okay, and that's what I'm saying. Strong duality holds in practice for many STPs. Okay, this is just reiterating the point I just made. STP duality theory allows for bounding alpha from both above and below. And indeed, this is a feature that we make use of in the QSlack method, with the idea being to provide certified bounds on the optimal value. Okay, I want to have a little discussion of quantum mechanics back to the foundations of quantum mechanics and semi-definite constraints. If you view the postulates of quantum mechanics from a purely mathematical perspective, you can say, well, you just apply some constraints to positive semi-definite matrices, and then you get all the fundamental constituents of the theory, right? So all the constituents of quantum mechanics, you can describe them mathematically as constrained positive semi-definite matrices. So it's very natural that quantum mechanics will intersect with semi-definite programming theory. For example, a density operator, what I'll call a quantum state, and I'll use this notation D for the set of density operators. Not only is it positive semi-definite, but it has this affine constraint where the trace of rho has to equal to 1. And that is related to the Born rule, the probabilistic interpretation of quantum mechanics, right? Where the outcomes of experiments are described by probabilities. Related, a quantum measurement is a set of positive semi-definite operators. This is often called POVM, which is short for positive operator valued measure, positive operator valued measure. And the positive operator is the same as being a positive semi-definite matrix. So a quantum measurement consists of a collection of positive semi-definite matrices with a constraint, the constraint being that the sum of these matrices is the identity, again, consistent with the probabilistic interpretation of quantum mechanics. There's also something, this is maybe a more advanced concept, quantum channel describes an evolution of a state. You can think of it as it's a super operator, so a linear map on states that takes a density operator to a density operator. And that's the basic idea behind a channel. And this can be used to describe all evolutions, including unitary evolution, which is the standard ideal kind considered for quantum algorithms. So the point I'm making here is that even a quantum channel can be described in terms of a positive semi-definite matrix with a constraint. This right here is something called Choi matrix, and it's constrained to be positive semi-definite. I won't use that concept further later, so I won't explain any more. But this is something that you can learn about if you consult a book on quantum information theory. Okay, so as I was saying, it's very natural for SDPs to play a role in quantum information. And what we're doing now, and so that's what people have done. There's various things that we want to optimize in quantum information science. For example, how much data can we communicate over a quantum channel? To figure that out, it's possible to phrase the problem as a semi-definite program, and then optimize over the set of states that are input to a given channel, and with some objective function. STPs have come up in quantum algorithms to analyze their complexity. It's come up in quantum complexity theory to understand how difficult certain computational problems are if you have a quantum computer. They come up all over the place. What we're doing now is we're flipping this. We want to use quantum states and quantum measurements, things that you can implement on a quantum computer to help solve semi-definite programs. So we're kind of flipping this around in this project. Okay, to give you a very concrete example, and perhaps the most prominent example that has been considered in the literature on variational quantum algorithms, if you want to find the ground state energy of a Hamiltonian, a Hermitian matrix, mathematically, this is a semi-definite program. You can minimize this objective function over the set of all states. So the state is positive semi-definite with trace equal to 1. As it turns out, since this is a linear objective function and the set of density matrices is convex, you can replace the optimization over all mixed states with an optimization over pure states. And that's what's commonly considered and done with the variational quantum eigensolver. But when we write it this way, we can understand it as a semi-definite program. So once we do that, and if you're familiar with semi-definite programming theory, which we just reviewed, there's going to be a dual, right? There's a dual STP. And if you run through the mathematics you can then determine that the dual STP has this form. And here it's trying to calculate the minimum eigenvalue of H. And then this is an alternate way of calculating the minimum eigenvalue of H. So it's trying to find the largest real number such that this matrix inequality holds, such that when you take H and subtract this from it, you get a positive semi-definite matrix. From the duality theory, we know that the dual will be less than or equal to the primal. In this case, I'm making the primal have a minimization. I'm making the dual have a maximization. The names primal and dual are just kind of labels. You can flip them around. It doesn't really matter so much. In this case, it's actually possible to prove that strong duality holds, so you get an equality. So one of the perspectives that we brought to the variational quantum eigensolver is to use the dual STP and try to calculate this dual STP using a variational quantum algorithm. As far as we're aware, that was original to this VQE literature. Okay. And of course, there's so much interest in this problem because it's of interest in condensed matter and chemistry to calculate the ground state energy of a given physical system described by Hamiltonian H. Okay, another example is the normalized trace distance. This is an example coming from quantum information science. Trace distance is a measure of distinguishability between two quantum states. The motivation for it is, suppose you have some process that generates a state, and it's not, you're trying to approximate some ideal process, right? Like maybe you're trying to generate a Bell state, and you can only do it in a certain way in the lab, and you instead make a mixed state. Well, then you want a way to compare how good is your experimental procedure versus the ideal mechanism to generate the state. So trace distance is a way to do that. And it's given by this formula. You take rho and subtract from it sigma, and then you compute what's called the trace norm, which is mathematically just the sum of the absolute values of the eigenvalues of rho minus sigma, okay? And then we put a 1/2 in front, and that will make sure that this number is between 0 and 1. So that's why I call it normalized trace distance. So if you run through some mathematics, which I'm not presenting, you can show that the trace distance can be rewritten as an optimization problem, right? And this optimization problem is a semi-definite program. You optimize overall lambda that are positive semi-definite, subject to this constraint that is less than identity. And so when you have these two constraints, you can interpret lambda as a measurement operator, and then you compute the difference in these numbers. So trace of lambda sigma can be viewed as the probability that you'd obtain the outcome lambda if you did a measurement, and trace of lambda sigma is the probability you obtain the outcome lambda if you did the measurement on sigma. And so this formula actually gives an interpretation of the trace distance as the largest difference in probabilities that could be observed by any experiment conducted on rho and sigma. And so if that's small, then rho and sigma are, in that sense, close to each other because they're physically indistinguishable by any measurements. So that's the primal. And then you can run through some mathematics, and you'll get the dual STP as this form. And so it's a minimization over positive semi-definite Z, this objective function, such that this constraint is satisfied. And, if you can actually prove that the optimal Z is the positive semi-definite part of rho minus sigma. So that's another example of interest in quantum information. This example we considered in the QuCS paper. In the interest of time, I'm just going to present one example. Okay, we have to proceed at a bit more rapid pace due to time constraints. With QuCS, there are really 4 key steps, and these are the key things I want to illustrate beyond the review of semi-definite programming theory, and which is like one of our core theoretical contributions. Just give me a minute. I have a cough and I got sick recently. Okay, so there are 4 key steps, and we're going to focus on the primal STP. Okay. The first key step is to introduce what's called the slack variable, and that's why we gave it the name, the shorthand name, QSlack. So this was our original primal optimization problem. What we want to do is replace this inequality constraint with an equality constraint, okay? And we can do this. What we're going to do is introduce a slack variable, W, which is positive semi-definite. As I said before, this inequality constraint here is equivalent to B minus phi x being positive semi-definite. Well, that statement is equivalent to the existence of a positive semi-definite W such that this equation is satisfied. So once we make this observation, we can introduce the slack variable W, and then these 2 optimizations are equivalent. And this is something quite standard that's done in linear programming and semi-definite programming theory. So there's nothing so original in this first step. However, it's critical for the conclusion we want to arrive at the end. Okay, so that's our first step. Second step is we're going to introduce a penalty term. So what we want is, now we have the optimization like this. We want to make the optimization an unconstrained optimization, and that will involve bringing this constraint into the objective function, okay? And so our next step is to take that equality constraint that was there and put it into the objective function where the C is a penalty constant. So this right here is a norm that's called Hilbert-Schmidt norm, or also 2 norm. And the key property that we need is that it's equal to 0 if and only if the operator inside is equal to 0, which is the same as B minus phi x being equal to W. Okay? And then if the equality constraint is not met, then you incur a penalty. This amount is subtracted off from the quantity you're trying to optimize. So if you don't meet the constraints, then you get penalized for that. And this is the penalty term allows for accounting for the constraints in this way. Okay? And a well-known result from optimization theory is that if we take the limit of this quantity as the penalty constant gets very large, then we approach the optimal value. And that's just the basic idea there, is that if you don't satisfy this constraint, the constraint that B minus phi x equals W, then you get like infinitely penalized. And so you might as well follow the constraint, which is like following the rule of a commander or something like that. Okay. And in simulations, we cannot take C to be, going to infinity. So what we do instead is when you're doing an optimization, you start with like a small value of C, and then you increase the value of this penalty constant to something that's quite large, such that you're approximately satisfying the constraint. So this is something else that we do, but again, this is something quite standard in optimization theory, and it's present It's reviewed in many books in optimization. Okay. So the next thing that we do is more original. You won't find this in an optimization textbook. So every positive semi-definite operator, if I divide x by its trace, it then becomes normalized. Let's call that resulting operator x prime. So x prime is x divided by trace of x. Well, then that x prime is a density operator and satisfies the postulates of being a state in quantum mechanics like we reviewed. So the next idea, so what I just explained tells you that every positive semi-definite operator can be written as a scaled density operator, right? So we can always, if I have an x, then I can always find a density operator rho and a positive scalar such that x equals lambda rho. So then we do that substitution here. We do a similar thing for w, and then we get this optimization problem. Okay, this is an equality because of what I just said. We're just doing a substitution, and the optimal value will not change under the substitution. When we do this, this then gets us closer to what QuCS is doing. Okay, and how we would implement this on a quantum computer. Okay, and I think now it's appropriate to make the comment on why we chose the 2 norm. The main property that we need for the penalty term is that it's equal to 0 if and only if the operator inside is equal to 0. So there's a wide variety of norms that we could use. The 2 norm is very good for quantum computation because the 2 norm of density matrices, and when you have various cross terms you'll get when you multiply out this norm, all those terms can be efficiently estimated on a quantum computer if B corresponds to an observable that's efficiently measurable, and rho and sigma are efficiently preparable states. Okay, so that's why we choose the 2 norm. And then again, in the limit, as this penalty constant goes to 0, we get the optimal value of the STP. So that's step 3. The final step, if you're familiar with variational algorithms, maybe it should be pretty clear what our plan is. We simply replace the optimization over all density matrices, over all quantum states, with parameterized ones. It's impossible to optimize over all possible quantum states because there's simply too many of them, and many of them, or let's say most of them, are not efficiently preparable on a quantum computer. So what we do instead is restrict to those that we can efficiently prepare by some parameterized quantum circuit. And then this is now the quantity that we try to estimate on a quantum computer. So this objective function is something that we try to estimate. And I'll get to that in a minute about that. Okay. So mathematically, since we've restricted the maximization to be over a smaller set, this alpha tilde is going to be, it cannot exceed the alpha when we optimize over all possible states. And so this inequality holds. And this is what leads to our lower bound on the primal STP value. Okay, so those are the steps for the primal. I think I have like roughly 15 minutes. We started 5 minutes late, so maybe I should try to just wrap up in 10 minutes. But those are the main ideas behind QSLAC. I'm just going to state briefly, this might look like a bit messy. You can do the same things for the dual. Okay, so you can go through the same procedure, and I'll just state it briefly here. Replace the inequality constraint with an equality constraint by means of a slack variable. Bring the constraint into the objective function. by means of a penalty term. And so now we have an unconstrained optimization. Replace the optimization over all positive semi-definite operators with scaled density matrices. So we have this. And then finally, replace the optimization over all quantum states with parameterized ones. Then we get the dual. And so this is the dual form of QSLAC. And again, as we take the limit of beta C with C going to infinity, we get the dual optimal value. This is a figure in our paper that summarizes the technique. I guess I've already stated it. It might be helpful just to review it very briefly again. This is the original SDP for the primal. This is the original SDP for the dual. Weak duality holds. Alpha does not exceed beta. For most cases of interest, this will actually be equality, and the condition of strong duality will hold. So for both the primal and the dual, the first step of QSLAC is to introduce slack variables to make inequality constraints to equality constraints. Then we bring the constraints into the objective function via penalty terms. For the primal, we subtract the penalty since you're trying to maximize. For the dual, we add the penalty since you're trying to minimize. Then in both the primal and the dual, we replace positive semi-definite matrices with scaled density matrices. And then the final step, so that we can actually try to do this on a quantum computer, is to use parameterized states. Okay. And the idea from here will be to use what is well known in variational algorithms. Methods like, you estimate this quantity and this quantity on the quantum computer, and then you use a feedback loop with a classical optimizer to select the new values of the parameters. And then you iterate until convergence. A key theoretical insight from QSLAC is that if in fact we could compute the optimal value of the simplified objective function and take the limit as the penalty constant gets large, then this alpha tilde would be a certified lower bound on the optimal value. And similarly for the dual, if we can in fact compute the optimal value of the restricted optimization where it's over parameterized states, then this would be an upper bound. And so the idea is to sandwich the true value from below and above, because in practice, the optimal value is not going to be known. But then when we do the simulation or the experiment on the quantum computer, and we find that the upper bound, the lower bound and the upper bound are close, then we actually can conclude that we're doing a good job of finding the optimal value. So that's the key insight of QSLAC, which distinguishes it from other work on variational quantum semi-definite programming. Okay. There's a question of how do you parameterize mixed states? When you look in the literature on variational quantum algorithms, you typically see parameterized pure states. That's what's used in the traditional VQE algorithm. So how do we optimize over mixed states, or how do we parameterize mixed states? Well, a first method is to use something that we call purification ansatz, and that follows from the purification principle in quantum information, that every mixed state can be viewed as the reduction of a pure state on a larger system. So what that means mathematically is I could take a pure state of qubits in a system R and qubits in a system S. The 0 is a shorthand for like 0 tensored 2n times. And then you'd act with a parameterized unitary on all 2n qubits and trace over the reference system R. And then you end up with a mixed state on the system S. And so this procedure requires 2 n qubits to make a mixed state on n qubits. And so there's a concern with this method that maybe you're using too many qubits. So that motivates a different method called the convex combination ansatz, and that uses the idea that every mixed state can be written mathematically as a convex or probabilistic mixture of pure states. And so the idea here is to make a mixed state, make a parameterized mixed state in a two-step procedure. So first, we would sample a value, a bit string X, randomly from a parameterized neural network that's described by this probability distribution. And then once you've done so, you would prepare the quantum computer in the state specified by the bit string X and act with the parameterized unitary. And when you do this, the resulting mixed state is described as such, right? So you're parameterizing both the neural network, the classical neural network, and the unitary. And you get a mixed state in this way. The advantage of this approach is that fewer resources of the quantum computer are needed. You only need n qubits to make this mixed state. And so that makes it a bit more interesting for, let's say, near-term applications. Okay, so to execute the QSLAC method on a quantum computer, for this to really work, we need to make an assumption, because it's not going to work if A and B and phi are completely arbitrary. So the assumption that we make, and we can think that A is an observable that acts on n qubits, right? And so if you have an n qubit state, you can measure this observable A. And so an assumption we make is that it should be efficiently measurable in order for this to have any hope of working well on a quantum computer. So we make that assumption for A, B, and phi, and then a quantum computer can measure all the terms in the objective function efficiently using either standard approaches for estimating expectations of observables, or by a procedure that's known in the literature as destructive swap test. I'm not going to review these two approaches due to lack of time and focusing on other things, but these are things you can look up. We reviewed it in our paper, and you can find various papers that show you circuit diagrams of how to do this. Okay, so with these assumptions in place, the idea is that in general, it's not clear how to do these steps efficiently on a classical computer, okay? So this kind of statement is where things become dangerous, right? Where, like, IBM released a paper, evidence of utility on a quantum computer, and then the next week there were these extremely impressive classical simulations, right? And so there's always a race between quantum and classical as to whether there's a true quantum advantage. But here the hope is that there will be some examples of matrices for interesting problems for which we can evaluate the objective function efficiently on a quantum computer, and it would be hard to do so for a classical computer. But that's very tricky and tough to prove, and that's where most of these Twitter debates are occurring for this kind of statement and claim. So all I'll say is that it's our hope that this approach might give a quantum advantage, but it's something that will only be able to be answered as we have better and better quantum computers, let's say, over the next 10 to 30 years. Okay, so to do the optimization, you estimate the objective function as well as its gradient You can do that using standard techniques in the literature. For the gradient, we use something called the parameter shift rule, or there's another method called simultaneous perturbation stochastic. Maybe that's ansatz. I forget what it means. Sorry. But it's known as SPSA, and it's a famous algorithm. Or I think it's approximation. So that's a famous algorithm that's used to estimate gradients. And then you can employ, there's all kinds of variants of gradient descent that can be used. And so we did a number of things in our paper, but we certainly didn't explore all kinds of things. One possibility, I was very impressed by a method called natural gradient descent. I was impressed so much that I introduced a whole lecture about it into my quantum computing course this past semester. So that's something we have not yet tried out experimentally. All right, in the remaining time, I want to illustrate applying this method to the ground state energy problem. And, this is the primal that's always considered in the literature on VQE. This is the dual, which is not considered as much, if at all. And for the minimization, you can apply the VQE method, right? And as we said, VQE, because you're doing a minimization, you're coming at the optimal value from above. And so it provides an upper bound on the optimal value, but the quality of the bound is unclear. So to serve as like a quality check on the bound you obtain from VQE, you can optimize from below. And that's the idea of QSLAC applied to the VQE problem, which is what we call dual VQE. See something in the chat. There was a question from Grace. Does the parameter shift rule have much larger cost than SPSA? Yes, and that's why in our examples we consider SPSA. Complexity of QSLAC over classical methods. That's a very good question. The complexity is we did not do a direct comparison in our paper with the best known classical methods. We consider that a question that we'll address in the future. Okay, thank you. Let me continue with this example. So very briefly, if we apply the steps of QSLAC to the dual problem for VQE, then that's inequality constraint, introduce a slack variable, become an equality constraint, replace with a scale density matrix, bring the equality constraint into the objective function via penalty term, and then replace with parameterized states. So we can do that, and then we get this lower bound of the optimal value. And if you work out, the terms, so this norm you can expand using its definition into 6 terms. And when you do that, you get this. You get these 6 terms. And this is very interesting. So suppose that your Hamiltonian is the common form considered in the literature, which is like a linear combination of Pauli matrices. Well, this you can then just calculate by hand. It's not hard to calculate. The same for the trace. Now you can calculate by hand. This is just a scalar. This is also just a scalar. So what you're left with is this term and this term. So what I was saying is that various terms can be pre-computed or easily calculated. This one, this one, this one, and the last one fall into that category. This term, interestingly, even though it involves the mixed state, when you use the convex combination ansatz, it actually reduces mathematically where it's just a function of the probability distribution. And so there's no need to use the quantum computer to evaluate this. It can be estimated by classical sampling. And that leaves just one term that you need to use the quantum computer for to evaluate to estimate it. And this term is very similar to the term that's used in the traditional VQE algorithm. And so, for a single run of estimating this term, its complexity is no more than that of VQE. However, a key point to stress is that the optimization landscape changes a lot because this is the optimization function now for dual VQE. And so that could lead to a larger complexity, and that's what we found in our numerical experiments. Okay, so, I made this statement of overhead using the quantum computer is the same as VQE. It's subject to the caveat that I just stated. When I was saying that, I really meant like estimating this term for a single run is no more complicated than the same task for VQE. Okay, so some examples. Right now, due to various limitations, we've only considered a 2-qubit simple example. We do want to scale this up quite a bit more, to be comparable to other simulations in the literature that are in the order of like 10, 20, 50 qubits. Jay Gambetta's standard at IBM is 50 qubits or nothing. So we're hoping maybe at some point we could meet his standard. This is showing you the results of these simulations. This is for the purification ansatz. The optimal value we can compute by hand. It's simple, right? And so that's this true value. If we use VQE, it converges relatively fast. It's coming from above, right? It's trying to minimize, and so it's coming from above, trying to get closer to the minimal value. With dual VQE, we come from below, right? And the convergence is slower, and that has to do with reasons that I mentioned before. I'll get into them more in the next slide. And this is the same optimization problem, but now using the convex combination ansatz, which in this example appears to converge more slowly, but still, after a sufficient number of iterations, it does converge to the optimal value. Okay, so indeed in our simulations, VQE converges faster. Possible reasons for this, as we said, the dual VQE objective function is more complex. It involves this, what we call global term. This can be rewritten in terms of a global observable acting on the state, 2 copies of the state omega. And, there's analytical work in the literature that shows that can lead to slower convergence. We're also doing an optimization over mixed states instead of pure states. And so these are just sort of ideas for why it's converging slower. More theoretical work could be done to help illuminate that. Also, the optimization landscapes are going to be quite different for VQE and for dual VQE, and they can lead to different resource requirements. Okay, starting to run out of time. Actually, I think I have run out of time. Maybe I'll just mention briefly, this is like the tax you have to pay whenever you write any paper on variational quantum algorithms. You have to acknowledge the barren plateau problem. So it exists for variational quantum algorithms for various reasons. One is if you randomly initialize your parameters, then the barren plateau problem can come into play. And that happens when the gradients of cost functions vanish exponentially with the problem size. And so it just, like the landscape becomes flat. That's why it's called barren plateau. And so it takes much longer to converge, and you might not ever converge. And so it's a big problem. There have been various proposals for overcoming this problem. In classical machine learning, it's extremely powerful, as we see when we log onto social media and we see all the things about Chat GPT and these images that are generated by AI. And so that problem is not there. And so there's hope that this problem can be overcome. Very recently, this was posted a while ago, but very recently it was published, and there was a nice Twitter thread from the lead author, Manuel Rudolph. The idea behind this approach being to use a classical simulation via tensor networks and powerful methods of neural networks to try to get a good initial point for the quantum algorithm. And then once you have that good initial point, the quantum algorithm can help to get an even better answer. And so this was very interesting. They had simulations going up to 100 qubits, which was very impressive for me to see in comparison to the 2 qubits that we have now for QSLAC and dual VQ8. So we strongly suspect that this idea at least could be tested out and applied for dual VQE, and we think it might be helpful. And more generally for constrained Hamiltonian optimization. But it's not clear to us how to apply this method when quantum states are the inputs of the problem, as is the case for trace distance. Okay, so in conclusion, QSLAC, we view it as a general method for bounding the optimal value of an SDP from above and below. In this work, we considered parameterized circuits for generating mixed states. If there are other methods like quantum Boltzmann machines, and there are methods for generating the states described by quantum Boltzmann machines, those can be used and can be tested, and they might not be subject to the barren plateau problem. A key aspect of QSLAC is that the terms in the objective function can be efficiently estimated if the SDP inputs A, B, and phi are efficiently measurable observables. And I showed the method for you in the ground state energy problem. Future directions, we want to determine the behavior of QSLAC for finite values of the penalty constant, right? So, for the moment, we're just kind of adopting this experimental heuristic approach. It would be nice to get more solid theory backing that up. Perhaps there would be existing literature in the optimization, existing ideas in the optimization theory literature we could take advantage of. One thing we definitely want to do, which I already mentioned, is scale up the simulations to more qubits. Do it on actual quantum computers. I should mention that these were just done using simulator on Qiskit and QLACs. So we want to do this on real quantum computers, incorporate error mitigation. A whole different idea is there's another method for semi-definite programming called the interior point method. It's another method for optimization called interior point method, which is very different from the penalty method. And so we'd be interested if it were possible to modify the QSLAC approach to be an interior point method. Thank you. I'll stop there.